Imagine you're protecting your most valuable possession. You wouldn't rely on just a single lock, would you? You'd have multiple barriers, a security system, reinforced doors, maybe even a safe. Each layer of protection makes it exponentially harder for an intruder to reach their target. This is the same principle behind defense in depth. That security architecture, which is like an onion that has multiple layers that protect its core. Modern enterprise security uses multiple defensive layers to protect critical applications. Today, I'll show you how to implement this approach in Azure, even when dealing with legacy applications that can't be refactored. And here's the twist. What if your application is fundamentally insecure? What if it's riddled with vulnerabilities like SQL injection, cross-site scripting, path traversal attacks? Can you still protect it? The answer is absolutely. Yes, and I'll prove it. Let me set the scene for you. You're the cloud architect for a big company. Your CEO just walked into your office with a mandate that we need to move our critical legacy applications to the cloud. It processes millions of transactions daily, but here's the catch. The development team that built it is long gone. The documentation is incomplete, and the application is running on end-of-life infrastructure. Oh, and we need it done in 3 months. This scenario is more common than you'd think. Companies have business-critical applications that are essentially black boxes. They work, they make money, but they're built on outdated frameworks with known security vulnerabilities. Refactoring isn't an option due to time, budget, or risk constraints. For our demonstration today, I'm using the OWASP Juice Shop. You can Google that and you can grab the software directly from them. And this application is an intentionally vulnerable web application containing over 100 security vulnerabilities. This perfectly represents our legacy application challenge. It's vulnerable by design, just like many real-world legacy systems. Just a quick note that OWASP stands for Open Worldwide Application Security Project. And they're the ones who developed this application for testing and learning security vulnerabilities. A typical security scan of this application would light up like a Christmas tree. SQL injection, cross-site scripting, authentication bypasses, you name it. In the old world, this would be a nightmare. But with modern Azure security services and the right architectural approach, we can make this vulnerable application enterprise ready without changing a single line of code. So how do we solve this? The answer lies in defense in-depth architecture using Azure's enterprise security services. Let me walk you through the solution I've designed. First, we implement a hub-and-spoke network topology. Think of this as creating security zones within your cloud environment. The hub contains shared security services, while the spoke isolates our application workloads. The traffic flow is carefully orchestrated. Internet traffic hits our Azure Application Gateway with Web Application Firewall or WAF v2 for protection. Then it flows through API management, running in internal mode, and finally reaches our containerized application in a private network. Each hop adds another layer of security. This is all deployed using infrastructure as code with Terraform. Now, let me explain how each security layer works. Starting from the internet edge, the first layer is the network perimeter defense, where our first line of defense is the Azure App Gateway with WAF. This isn't just a load balancer. It's a security appliance that inspects every HTTP request. Let's first have a look at the WAF policy. Under Manage Rules, we've turned on OWASP 3.2, which has protection against the top 10 web application vulnerabilities. And as you can see, there's a lot of rules here that are managed by OWASP for us. We have this custom rule for blocking malicious IP, saying if the IP address matches these IP ranges, then deny traffic. We've got another rate limiting rule, which says that within a duration of 1 minute, if there are more than 100 requests from a single client address, then block that or deny that traffic. Then this is associated to the application gateway. And more importantly, this application gateway is configured to send its logs over to a log analytics workspace, which I will demonstrate later how we can look at the logs to tell us or to inform us what is being blocked by the firewall and what rule it is applying. The next layer, layer 2, is our API governance layer. This is the critical bridge. Now, you might be wondering, why not connect the application gateway directly to our application? If we go back to our architecture, you can see application gateway here with a backend of an API management service, which then ultimately sends the traffic to the application, which is a container instance. This is our vulnerable legacy application. So we're using API management in this case because we want that extra layer of protection and for governance. I'm going to explain this using analogy, and hopefully it will make it clearer. Think of your architecture like a medieval castle defense system. Without API management, you have a single castle wall with a gate, so internet traffic hits your application gateway outer wall. If someone gets past it, they're directly at your treasure. This is your application, which is hosted on a container instance. With API management, you have multiple courtyards with specialized protection or a guard at each checkpoint. API management acts as our inner courtyard, a sophisticated checkpoint between the outer defenses and our vulnerable legacy application. Here's why this layer is absolutely important for legacy application protection. It acts as an API translation layer. Your old application can speak some ancient language, weird URLs, odd parameters, legacy authentication. With APIM, it translates modern API calls into whatever your legacy app expects. For example, modern clients call /API/users, but your legacy app is expecting something different, like /legacy/get-user-list.php, for example. Here's what we've set up for the Juice Shop API. We have several APIs for it. It does a get, which ultimately sends it to the backend container instance. In this case, because my application already uses RESTful API, there's not much transformation. There's no transformation being done. So one thing I'd like to point out that is very important in the configuration between the app gateway to the API management service, if you notice the backend pool, this is configured to route the calls to the app gateway to route it to the IP address of the API management service. Okay, so API management service, you'll notice it has two virtual IP addresses. It's been given a public and a private. The public, you can't reach it. Even if I try and hit the gateway URL, I'm not able to, because this public IP is only accessible by Azure services so that it can monitor the service and make sure it's running. This is because API management has been deployed and configured to be in an internal virtual network. What we can really use here is only the private IP address of 10.0.2.5. And that's how we've configured the routing from the application gateway so that when there's traffic that hits it, it will route to the backend IP address of the API management service. However, in the HTTP backend settings, we've configured it to send the HTTP host header to the backend using the host name of the API management service, the FQDN of APIM. Using this custom probe as well that we've created. So we're saying for the probe to make sure that it's healthy, use this FQDN address of the API management service. Now you might be wondering, why are we routing the traffic to an IP address, but we're setting the host header to an FQDN? This might seem contradictory, but it's actually a practical solution that I've used for this demonstration. Because here's what happens. The application gateway routes traffic directly to the private IP, but it sends HTTPS requests with the host header set to the APIM's default domain. This way, there's no DNS dependencies. I don't need to create a custom domain for my API management service and set the DNS record for that. APM validates the host header against its SSL certificate. So I can't use the FQDN without proper certificates being issued. For demonstration, it's just for quick setup. But in an enterprise environment where you have the proper DNS infrastructure configured, then you'd want to use FQDN all throughout, from the backend pool routing to your backend HTTPS settings and your health probe. Now, let me just explain a bit more. I want to use the analogy of a hotel with two addresses analogy to explain that concept. The APIM service, think of it that it is a hotel building. It has this FQDN address of AZNT azure-api.net. So when we think of it like a hotel name, it can be the Grand Hotel on Main Street. Then we are also using the private IP address of 10.0.2.5. And so you can think of this as GPS coordinates. It's the same building, but there's two addressing methods. One is the name, the Grand Hotel on Main Street, and the other is the GPS coordinates. Application Gateway is like our postman or our Amazon delivery guy. He knows the exact GPS coordinates, but it still writes the proper hotel name on the envelope. And what actually happens is when the mail carrier, the app gateway, is configured to do it this way, it drives directly using the GPS coordinates. There's no need to ask for convert the name of the Grand Hotel to GPS coordinates. It's direct. The driver then arrives at the hotel and hands over the envelope addressed to Grand Hotel on Main Street. When the hotel receptionist receives it, they will see that yes, it is addressed to us correctly at Grand Hotel on Main Street. And it is accepted by the receptionist because the name matches their business license. In our case, this is the SSL certificate. Finally, we get to our application, which is hosted in this container instance. And as you can see, it's got a private IP address. It is hosted in another VNet, which is a spoke VNet, peered to our hub VNet. So this container instance is isolated in a different network, in our spoke network, with its own subnet with a security group that allows only API management to access the container, saying that the API management subnet, so the subnet IP, is allowed to access port 3000, which is where our application is hosted. Anything else is denied. We have our certificate that I've used to configure the application gateway, and it's hosted here in Azure Key Vault with our Azure Key Vault, which should be disabled from public access and can only be accessed from a private endpoint. For the purpose of this demo, I've turned it on to allow public access from all networks so that I can show you the certificate. If we try and navigate to the app gateway front end, it will alert us with a certificate authority invalid because this is a self-signed certificate. You'll be able to see that in the certificate details of your browser. It's not issued by any well-known certificate issuer. As you can see, it is self-signed certificate issued by itself with a common name of itself. Now for the exciting part. Let me demonstrate the difference between accessing our vulnerable application directly versus through our secured architecture. I will be accessing a VM in the same VNet as our app gateway because the container instance, as we've seen, can only be accessed privately. So our virtual machine has a public IP address, which is where I will be SSHing to. We'll just quickly access the URL, which is our juice shop. You can see that if I make a curl call to ipinfo.io, this is my public IP that I'm accessing from. I'm just going to populate these variables. So this is my container IP. Let's SSH into my debug VM. I want to show you the vulnerable application by directly doing an SQL injection. So we're going to make this curl call, which is this is a well-known SQL injection attack. After you have selected the original query of Apple, you add in an OR statement for 1 is equal to 1, which is always true. And we're going to hit the containerized application directly. So we can see it's a successful SQL injection attack. Let's now try a cross-site scripting test. Again, I get a successful return. The payload that I've sent through went unfiltered, and in a real browser, this would execute JavaScript. Next, let's try and do a traversal test. And we can see some potentially sensitive files that should be protected. The name, version, description, what my homepage is, etc. Now I'm going to try and do those same attacks through our WAF protected application gateway. This is our application gateway FQDN, and this is the path to our juice shop application. If we try and do our SQL injection, we're getting a 403 forbidden error. Now let's try to do the XSS protection, and we're getting the same. It's blocked again. Lastly, we'll try the path traversal protection, and it's failed again. Every single vulnerability we exploited directly is now protected. And here's the real magic. We can see all these blocked attacks in real time through our monitoring dashboard, which if we go to our logs and we'll just run this, this shows us all the logs. We can see our firewall log. The request URI is the last call we've made directly from my laptop doing the path reversal attack. It used this rule group request 920 protocol enforcement using the rule type of OWASP CRS version 3.2. Then if we look at the next one, so it is assessing the same path that we used in the last call with a different message saying invalid character in the request, non-printable characters. So it doesn't like that. It used, again, this rule to apply and block our attempted attack on the application. This path is the second call we made, and this is the XSS protection attack that we've tried to do via a lib injection, which the system has picked up. And it's my client IP address and what the rule it used with some messages that will help our security team assess what is going on when a particular access has been denied. And here we can see the WAF manage rule matches in the last 24 hours. There's already been a lot of blocks and attempts to the application. So it's not just me trying to access it, but a lot of other bots all around the world trying to make a sweep of any applications that may be vulnerable to known attacks. Today, we've demonstrated how to transform a vulnerable legacy application into a secure, enterprise-ready system using Azure Security Services. The key takeaways are defense in depth, multiple security layers that provide redundant protection. Zero trust architecture, never trust, always verify. We've implemented network segmentation or isolated workloads with private networking, setting up WAF protection by blocking attacks before they reach applications. Secrets management, where we have a centralized certificate and key management system. Infrastructure as code, creating reproducible, auditable deployments. Continuous monitoring, real-time visibility into security events, and comprehensive logging and alerting. This architecture provides a proven path for securing legacy applications in Azure. The key is implementing multiple layers of security so that when one layer is compromised, the others continue to protect your valuable assets. Remember, in building a secure cloud solution, it's not about building a fortress that is impossible to get through. It's about making your systems so difficult to attack that those with bad intentions, they just decide to move on to easier targets. With Azure's security services and the right architecture, you'd be able to achieve exactly that.